All right, hello everybody. So we're going to look at two kinds of self-balancing binary search trees, and the first one is called AVL trees. AVL is like the creator's initials. I can't remember their names. It's like Russian or something like that. Anyway, so AVL trees are a kind of self-balancing binary tree. So as you insert and remove things, the tree sort of like checks to see if it's still balanced and adjusts itself if it's not. The sort of formal definition of an AVL tree is a normal binary search tree with an additional height balance property, which just says that if you look at any node, the difference between the heights of its left and right subtrees is never more than 1. So if you want to do it in like sort of mathematical form here, if you take the absolute value of the height of the left subtree minus the height of the right subtree. That's what these little vertical bars here are for, like absolute value, right? Absolute value, absolute value. That absolute value should always be less than or equal to 1. It's actually going to be either -1, 0, or +1 there in a valid AVL tree there like that. So we allow for a little bit of imbalance here just because, you can never sort of, it's rare to be able to get a perfectly balanced binary tree here, but we don't allow for too much imbalance. This height balance property applies everywhere, like not just at the root here. So I'm going to draw the heights of the trees in this sort of like purple color underneath the nodes here like that. So that's the height of that sort of subtree. So the height of the whole tree is 4. From the top down to the very bottom, right? It's 1, 2, 3, 4, like that. But we need to know the heights of the individual subtrees as well. So the height starting here at 12 and going down is 3. 1, 2, 3, like that right there. Or if you start here, right, the height of this subtree at 78 is just 2. 1, 2. We're actually going to store that information inside of the nodes here like that so that we always have easy access to what the height at anything is. But the point is, if you look at the heights in here, right, the difference between any two sort of siblings here is always plus or minus 1. So here it's like plus 1. Here it's minus 1, like that. Here to here, yes, null pointer nodes count, right? It's plus 1, like that. If you go, like sort of in different places, wherever you sort of compare siblings, over here, this to this, it's plus 1. That difference is always going to be either positive 1, negative 1, or 0 in the case of like a sort of perfect balance there like that, which this tree doesn't have. We don't want to spend a bunch of time recomputing the heights, so we're going to save the heights inside of the nodes. That will mean that like when we insert something or remove something, we will have to go through and update those heights and fix them based on that insert or remove there, but that'll give us sort of fast access to the heights there like that. And then the other thing we need to do is we need to walk up the tree, so we're going to store parent pointers inside of the nodes here. Now, you can actually get away with not having parent pointers. You can sort of use the recursive find and insert, and then use the fact that like recursion goes up when it's returning to sort of do what we need to do on the way up there like that. But it's kind of tricky and sort of fiddly, so it's easier just to store the parent pointers inside of the nodes there like that. So insertion and removal on an AVL tree, they start the same way as like on a normal binary search tree here. Only after we've actually done the insert or the remove does the AVL part of it sort of kick in here. So when we add or remove a node, that can affect all the stuff from that node up to the root of the tree. All of those things' heights might be wrong now because we've just added something underneath them there. So we have to walk up the tree and update all the heights in the nodes there like that. But at the same time, while we're doing that, we're also looking for imbalances. And imbalances are any place where we have siblings whose heights differ by plus or minus 2. Now, note that we don't have to worry about imbalances worse than 2, like 3 or 4, or anything like that, right? Because we know going in, we had either -1, 0, or 1. We only insert and remove one node at a time, so that could push us to a -2 or a +2, but as soon as we have an imbalance, we're going to fix it. We're going to turn it back into a plus or minus 1 there, so it'll never get worse than like a plus or minus 2 there like that. So those will be the kind of imbalances that we'll look at like detecting and fixing, are just plus or minus 2s there. So for example, like let's say that we want to insert 62 into the tree before here. So 62 is going to be placed down here as the right child of 59 there, like that. So I just added 62 down here, but notice that now the heights of the things above 62, that height, and this height actually is okay here, but like those heights, all of those potentially need to be fixed here like that. Like the 1 is wrong, it should be 2, 2 is wrong, it should be 3, 4 is okay because there's already a 3 on the other side there like that. So I'm going to have to start at 62 and kind of work my way up the tree here to fix those heights. At the same time, I'm going to look for imbalances. If I go up and I update this height here like this, right, I discover that I actually have an imbalance here between 59 and its null pointer sibling over here, right? 2 minus 0 gives me positive 2, which is greater than 1. So I have an imbalance here at 78, which we would have to fix. We'll see how to fix this imbalance like sort of later on here, but that's kind of how we would like detect an imbalance there. In order to fix imbalances, we need a way to kind of like tweak the shape of the tree without breaking the search order property here. So let's consider a sort of model situation where we have a parent node and a child node, and then some subtrees. Now, P is not necessarily the root, right? There might be more stuff above here. We're just kind of zoomed in on one particular part of the tree here like this, right? So if we have this arrangement, what do we know about C and P, and then X, Y, and Z here? Well, we know that C is going to be, that's wrong, less than P, and we know that P is going to be greater than C, like just because C is to the left of P, so that means it's going to be less than P, and of course P is up here. The inverse of that is going to be greater than C there, like that. Okay, what about X? We know that everything in X is less than C, and then by sort of inference, it's also less than P here. So X is all the sort of stuff that is less than C and P here, like that. This again is wrong. That should be less than P, like that, right? Likewise, what do we know about Z? We know that Z is all the stuff that is greater than C and P here. It's all the stuff that's sort of bigger than both of those there, like that. Right here. And then finally, what do we know about Y? We know that Y is all the stuff that is kind of in between C and P. So it's stuff that is greater than C, but less than P. It's sort of in the middle of those things there, like that. So if we want to change the shape of this part of the tree, we need to do so in a way that still preserves these relationships here. So let's say that we want to move C up so that it becomes the root of this subtree. Now again, this is not the root of the whole tree. There might be more stuff sort of above it here, but we want to change things so that C moves up to this position here like that. So based on that, where should the other stuff go? Well, P, remember what do we know about P? We know that it is greater than C, so therefore P is forced to go down here and become the right child, since P is greater than C. X is all stuff that is less than C, so it still stays over here as C's left subtree. Likewise, Z is all stuff that is greater than P, so it stays over there as P's right subtree. The only other thing that changes is going to be Y. What do we know about Y, right? Y is things that are greater than C but less than P. So in the new tree, that position is down here as P's left child there. So again, just to double check that, greater than C, yes, because it's to the right of C, but less than P, yes, because it's to the left of P here. So Y switches sides from being a right child of C to a left child of P. Right there, right? So these new placements, it's consistent with what we know about all of this stuff here, but it has the effect of moving C up while also moving P down. Now, of course, there's two versions of this rotation that are sort of symmetrical with each other based on whether C is on the left or the right of sort of P, but the idea is still the same here. We're sort of reshaping this part of the tree to sort of like move C up and move P down. A few just sort of other notes here, right? Like I sort of emphasized before, P is not necessarily the root of the whole tree here. It's just the root of the subtree that we're looking at. There might be more stuff above sort of P there like that. X, Y, and Z, those might be empty, like they might be null pointer there. The only requirement for rotation is that C exists and P exist here, and C has to be a child of P. That's it. Other than that, X, Y, and Z might not exist there. Y is the only subtree that we move. X and Z stay in the same place. Rotation is its own inverse. If we rotate C with P and then we rotate P with C, you just get back to where you started there. Now the important part for what we're doing right now is that when we rotate C, that moves C and X up while moving P and Z down, right? So that affects, that sort of like moves the height of the tree over from one side to the other side. So if I have a tree that's too heavy on one side, I can do a rotation and shift some of the weight over to the other side here. And then, of course, the last thing is rotation is just manipulating pointers, so it is a constant time operation. Here's the basic code for rotate here. These assertions here at the beginning are just sort of enforcing our requirements that C and P can't be null pointer, and C has to be a child of P there, like that. And then the core of it is just sort of two mirror image cases here based on the relationship of C and P. So if C is P's left, right, if we have like that, then that means Y is down here. So we're going to turn that into a new arrangement where we have C, P, and then Y down here. So Y is originally C's right, but then C's right becomes P, and then P's left becomes Y. Or, going the other way, if we have the opposite arrangement, right? If we have P, C, and then Y down here, then Y is C's left. C's left in the new arrangement here is going to become P, right? And then P's new right is going to become Y in the new arrangement. So we go from that to that arrangement there, like that. Now we might have to do some other stuff here. If we have heights inside of our nodes, we need to update those. If we have parent pointers, we might need to update those. But that's the core of the sort of rotation there. And again, it's just pointer juggling, no loops or anything, so this should run in constant time. One thing to note is some versions of rotation divide this up into two different functions that take just the parent pointer as their parameter. Our function takes child and parent as parameters there, and then sort of deduces their relationship from them. But some versions just take the parent and they use the name of the function to determine which child we're rotating. So here we're going to rotate with C arrow left, and here we're going to rotate with C arrow right, like that. The disadvantage to having two functions is everywhere that you want to do a rotation, you have to put in an if-else to determine like which one you want to do. So if we put that if-else inside of the rotation function, then we only have it in one place in our code here instead of having if-elses sort of scattered all over the place there. I just like sort of doing it inside of the function itself there. Okay, so let's say that we have a tree like this, and we have an imbalance here that looks like this. So we originally, in this case, we started with a tree that was just this stuff there, and then we inserted the -10, which pushed us into imbalance territory. Excuse me. We have this +2 imbalance between -4 and the null pointer there. So that means we would have an imbalance at node 12 there, like that. 12 is the place where we would discover this, because remember what we're doing is we're starting at the new node that we just added and kind of working our way up to the root, updating the heights as we go. So we're going to fix the first imbalance that we discover along this sort of path here, like that. So if we zoom in on this part of the tree here, and we sort of label things in the case of like the rotation, right? So this section down here, that is X. This null pointer over here, that is Z, 12 is P, -4 is C, and then this null pointer here, that is Y there, like that. So what are we going to do? We're going to rotate C with P. We're going to rotate -4 up with 12, which turns this into this shape here. So again, this chunk here, that is X, like that right here. This is P, 12 is P, Y is C. The sort of subtree that is Y is empty, and the subtree that is Z is also empty there like that. So that's why there's nothing sort of down there like that. And notice that after we're done, sorry, let me clean this up here a little bit, right? The imbalance is fixed. We went from an imbalance of +2 to an imbalance of 0 there like that. Now, if you go back and look at the original tree here, there's actually two imbalances. There's two places where we have a +2. We have 2 versus 0, but then if we go up, we have 3 versus 1 here like that. So why did we fix this imbalance here, the imbalance at 12, and not the imbalance at 45 there? We always fix the imbalance that's sort of closest to the bottom of the tree here, because fixing this bottom imbalance will also fix the imbalance above it. Like if we draw the new tree after that rotation, we have this tree here like that. So there is no longer an upper imbalance in the tree here. It's gone from being a +2 to just being a +1 there. So whenever you are sort of like working with AVL trees, you always fix the imbalance that's closest to the bottom of the tree. There may look like there's other imbalances, but they're not real. They're just sort of shadows of the lower imbalance there like that. Okay, so let's look at what kinds of imbalances we have to worry about here. So every imbalance we can fix with either 1 or 2 rotations, just depending on the type of imbalance. The imbalances that we just looked at, those are outside imbalances here, where we have sort of extra weight on the outside of the tree, so it's all on the left or the right there. We can fix those with a single rotation. Another kind of imbalance, which is the kind that we saw from the very first tree, is an inside imbalance here, and that's a little bit more tricky to fix here. But first, outside imbalance here. So the sort of abstract form of an outside imbalance is something like this here. So we have a parent node, a child node. We have an X subtree with a height of h plus 1. H is just a placeholder for whatever the actual height is, so maybe the height here is like 7. Y has a height of h, like say 6, right? Z has a height of h, which is 6. That would give C a height of 8, and then of course 8 versus 6 is +2, like that right there. Or the mirror image of this going in the other direction looks like this sort of shape over there like that, right? So what do? We rotate C with P, and that has the effect of sort of fixing the shape of the tree here. Right? So if we have this sort of shape here, we rotate C up with P, that gives us this tree here, and the imbalance is fixed. Or over here, we rotate C up with P, and that gives us this tree over here. Either way, the trees on the right no longer have any imbalances, right? We go from a +2 or -2 to a 0 sort of balance factor there like that. Now, how can outside imbalances occur? They could happen because we added something down here inside of X, or they could happen because we used to have something inside of Z, and then we deleted it, right? Either we made X 1 taller, or we made Z 1 shorter there like that. But either way, we can fix it with just a single rotation. Inside imbalances are ones where the extra weight comes from the Y subtree, the sort of interior part of the tree here like that. So our tree is too heavy in the middle rather than being too heavy on the outside there like that. So here we need a little bit more information. We have to drill down into the Y subtree. So now we're interested in a grandparent, a parent, and a child here. So C is the root of what used to be the Y tree, and we're going to break that Y tree into Y left and Y sort of right here. So we have this kind of arrangement down here. The heights of like the YL and the Y1, like it could be like H plus 1 and H, or maybe the other way around, right? Like H and H plus 1 or something like that. As long as they sort of give us an H plus 2 at the C there, that's what we're kind of interested in here like that, right? So we have our imbalance between here and here, +2 like that, but we've drilled down a level to kind of like see where exactly the source of the problem is inside of that Y subtree here, which again, the Y subtree is all of this stuff in here. All right. So we want to repair this. Let's think about what we want it to look like. So if we're starting with the thing on the left here, the most balanced that we could make that would be if we put C up at the root, right? And then we kind of spread everything around it as evenly as possible here. If we spread it out like that, we have 0 imbalance between there and there. So that would kind of set that up. And again, like we don't know whether this is h plus 1 and h, or maybe the other way around. But that doesn't matter, right? As long as I have an h plus 1 here and an h plus 1 here, I'm going to get an h plus 2 there and an h plus 2 there, like that. So what rotations will it take to go from this shape over here on the left to that shape over there on the right? It's not just one, it's 2 rotations. So I'm going to rotate C twice. So you notice that like in this sort of shape here, right, I want C to move up 2 levels from down here to its new home up there. So therefore I need to rotate C twice. This is going to be called a double rotation here. So if we do it sort of step by step here like this, right, I know it's kind of like small and sort of hard to see. So we're going to rotate C up once. That turns the tree into this middle shape here like that. Now notice that we haven't fixed the imbalance yet. So we have an imbalance from between there and there. Now we have an imbalance between there and there, like that, right? But then we do another rotation to move C up here, and now the imbalance is fixed, right? We're at a 0 between there and there, like that. So in the case of an inside imbalance, we do a double rotation. So the complete algorithm for AVL insertion looks like this. You just do a normal insertion, and then you start at the node you just inserted, and you're going to follow those parent pointers up the tree until you get to the root. So first we're going to update the height. We just set the height to the larger of its 2 children, whoops, plus 1. Don't forget about that, right? Then we check the balance factor, which is just the difference between the 2 heights there, like that. If it is -1, 0, or 1, that's fine. We allow those. But if it is -2, 0, or, excuse me, -2 or 2, not a 0, geez, there's a bunch of mistakes in this one, right? -2 or 2, right? Then there's an imbalance here. So then we check to see if it's an outside imbalance. If it is, we rotate one thing with P. If it's inside, we double rotate the heavier grandchild there, like that. To remove from an AVL tree, it's pretty similar. You do a normal removal, and then you start at the parent of the removed nodes. You walk up the tree, update heights, check for imbalances, blah, 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 like that right there. For an insertion, you'll only ever discover one imbalance, but for removal, you might have more than one imbalance there. So to kind of see like this in action here, let's insert these values into an empty AVL tree here. So I'll insert these values one at a time, and we'll write what the heights are here. Okay, so first 45 is here. 45's height is 1. All right, cool. That tree is balanced. Then 12 is going to go to 45's left. So now we have an imbalance of +1, but that's okay. We allow that, right? The height at 45 is sort of 2 there, like that. No imbalances yet. Now -4 goes over here. So now we have an imbalance. We have a +2 imbalance. What kind of imbalance is this? It is an outside imbalance at 45. 45 is where we'd look at our 2 children and be like, hey, wait a minute, 2 minus 0 is +2. That's an imbalance here. So what am I going to do to fix this? I'm going to, so P is there, C is there, rotate C up, which leaves me with this tree right here. This is the sort of final tree after inserting -4. 78 is going to go down here all the way to the right. So again, notice that we have a slight imbalance here, right? A -1 imbalance there. And a slight imbalance here, a -1 imbalance there. But with 4 nodes, you're going to have an imbalance somewhere. There's no way to make like a perfectly balanced tree with just 4 nodes. So we allow that to exist there. 59, though, goes down here. And then that means we now have another imbalance. We have a -2 here like that. It's important if you're doing this by hand to draw the null pointer nodes in, because it's really easy to miss the fact that you have an imbalance with a null pointer node there. So draw the null pointer nodes and their heights of 0 inside of it there like that. So now we would discover right here at 45 that we have some kind of imbalance. We would look at our children and discover that we have an inside imbalance here like that. What do we do for an inside imbalance? We are going to double rotate 59. So we rotate 59 once, 59 twice. This is the new sort of tree shape that we're left with here, right? So again, I have a slight imbalance here, a -1 imbalance here, but not big enough to cause me any problems. 30 is going to go down here. So now I have another inside imbalance now at the root. At the root, I would discover that, wait a minute, my children differ by 2. So I have an inside imbalance here like this. So just to label everything, this is grandparent, this is parent, this is child, down here like that, right? This is my X subtree over here. This is the Z subtree over here. This would be Y sub left, and this would be Y sub right, like that. So what are we going to do? We're going to double rotate 45. So after the first rotation, 45 moves up, and we're here. Now notice that didn't fix my imbalance, right? One rotation is not enough. We're going to rotate 45 again, which moves 45 up here. And now we're all good for imbalances, right? We have, again, like a slight imbalance down here at the bottom, but we allow that because with 1, 2, 3, 4, 5 nodes, there's no way to have a perfectly balanced tree. And then finally 39 is going to go there, which sort of fixes one of those little imbalances there like that. So we still have like a slight imbalance here, but that's okay. That's fine. Again, with this many nodes, 1, 2, 3, 4, 5, 6, there's no way to get a perfectly balanced binary tree. That is the final state of the tree there like that. All right. The analysis of AVL trees is a little bit kind of like, involved here, but I'll give a sketch of it here. It relies on some math that, like, we haven't covered and you probably haven't seen before, but I'll just kind of like wave my hands over some parts of it here. So what we're wanting to do is we're wanting to see what's the worst case for an AVL tree. What is the most unbalanced tree that we can make with the sort of still following the height balance property here. So we're looking for a tree, which we'll call TH, of height h with the minimum number of nodes here. So we're looking to create like the tallest tree that we can make with the smallest number of nodes, the most unbalanced tree there. So we know that TH is an AVL tree, which means that it has to be height balanced, right? So the heights of its subtrees have to be h-1 or h-2. At least one of them has to be a height of h-1 there like that, because again, we're trying to sort of make the minimum number of nodes here like that. So one of them should be smaller than the other. So one is h-1 and the other one is h-2, right? I have two subtrees and one of them is slightly smaller than the other there. So we have something like this, right? I have my two subtrees, h-1, h-2, and then this is a +1 that gives me a total height of h there. So the number of nodes in the tree is there's n sub h-1 in that tree, n sub h-2 in that subtree, and the total number of nodes is nh-1 plus nh-2 plus 1. If that looks familiar, it should, because it's kind of similar to the Fibonacci thing here. All it's missing is the sort of +1 that we have over here. So in fact, if we sort of like work out this relation here and line it up against the Fibonacci sequence, we see that 1 is just 2 minus 1, 2 is 3 minus 1, 4 is 5 minus 1, 7 is 8 minus 1. So the elements of our n sub h are just the Fibonacci elements minus 1 there like that. Now there's a mathematical property of the Fibonacci sequence that kind of like approximates the values, and it's like this gnarly looking thing here. So phi here, right, is the golden ratio, 1 plus √5/2. So the hth element of the Fibonacci sequence is going to be greater than phi to the h power over √5 minus 1 there like that. So what we're going to do is we're going to kind of like, wave our hands algebraically speaking and rearrange this stuff here so that we get something that we can kind of use here like this, right? So if I just kind of like sort of hit this around like that, I eventually end up with something that looks like this, that says that my height is going to be less than the log base phi of this gnarly looking stuff on the inside here. If I throw all of that inside of a big O, right, the +2 goes away, the √5 goes away, the base on the log goes away, the -3 goes away, and I'm left with the height is log of n there like that. If you want to, you can work through that sort of like step by step and kind of like see where all the bits come from, but that's the basic idea. It's sort of like the height of our tree is going to kind of follow a sort of Fibonacci sequence, and the Fibonacci sequence kind of follows like a sort of logarithmic kind of pattern to it there. Okay, so to sum up, AVL trees have this height balance property, which is reinforced after every insertion and removal. So the height of a tree is always a constant multiple of the log of its size. They're like that. Fixing the nodes requires an additional loop, but that's just another OH on something that's already O of H, so it doesn't change the big O runtime there. AVL trees are the contents of assignment 4, so if you want, you can take a look at the assignment 4 video now. But other than that, I will say, as they say in Canada, peace out.